Vector Calculus, Lecture 15. So we are in Chapter 15, and we're studying functions of several variables. So you might have a function z, it's a function of x and y, a function of two variables, or w, which is a function of three variables. And we've looked at partial derivatives and directional derivatives. And what I want to talk about today are the chain rule and gradients. And gradients are particularly important. And from the gradient, we'll learn something about the tangent plane to a surface. So let's begin. Let me just So geometrically, the important thing to remember is if you have a function of two variables, the graph is a surface in R3, which means three-dimensional space. So in the xy plane, if you have some function defined on some domain, the surface, the graph of that function, is some surface over that region. And we want to know at what rate does the function, let's say we're just looking at a function of two variables, z equal f of x, y, at what rate, at what rate does the function vary or change at a point x naught, y naught? And it depends on the direction you move in. So if you have a point x naught in this region, and here it is on the surface, you could go in the x direction, and the intersection of the plane, look at the line going through this point in the x direction, the graph is a curve in the surface. It has some rate of change in this direction. But if you go in the y direction, you get a different curve and a different rate of change. And there's no reason to pick just the x and the y directions. You can go in any direction. So let's just look at some simple example. Suppose we have f of xy is x cosine xy. If you fix y and take the derivative in the x direction, the rate of change is the partial of f with respect to x at any point xy. If you differentiate this function with respect to x, you get cosine xy minus xy sine of xy. If you fix x and take the derivative in the y direction, the rate of change is the partial derivative of f with respect to y at the point xy. If you differentiate this with respect to y, you get minus sine of xy times x squared. So in the xy plane, if you go in one direction, you have one rate of change in the x direction. In the y direction, you have a different rate of change. Suppose you go in some other direction. Suppose you take a line going in this direction of, let's say, alpha. This is the line y equals alpha x. And what is the rate of change in the alpha direction? So that is the directional derivative in the direction of alpha. And let's figure out what that is. So actually, instead of alpha, suppose we let u be a unit vector. That is, the length of u is 1. So in particular, u is not 0. And if you have a point, let's say AB, in the domain of the function, suppose u has coordinates u1, u2. So from the point AB, let's say this is the vector u, I want to take a line through AB going in the direction of u. So a point on this line will have coordinates a plus u1t, b plus u2t, right, for some t. Right? This is the equation of the line through the point AB in the direction of u. And if you want to find the directional derivative of f at the point AB in the direction u, we would take a point, a small distance along the line from AB. So let's say a distance h. So a plus h u1, b plus h u2, minus f of AB. That's the value here minus the value here, divided by the length of the vector from here to here. But the length of the vector is h times the vector u. The vector u is a unit vector. So that has length h. And we take the limit of this as h goes to 0. And this is, by definition, the directional derivative, capital D for derivative, in the direction u of the function f at the point AB. So this is the magic formula. And the question is, how can we calculate that? And there's one rule that simplifies this tremendously and allows us to reduce the directional derivative, d sub u of f, to the partial derivatives. D sub x of f and d sub y of f, or f sub x and f sub y, equivalent notations. And we obtain this direction by applying the chain rule. So let me review what is the chain rule for a function of 2 or 3 variables. So I'll do the chain rule, and then we'll come back to calculating that or using that to figure out the directional derivative. So the chain rule. Suppose we have z as a function of x and y, but x and y be differentiable differentiable functions of the real variable t. So x is a function of t, and y is a function of t. So I can have z is f of x, but x is put in a function of t, and y is a function of t. So this makes z a function of t. And the chain rule says, so this is a function now of one variable. So z is a function of t. So I can ask, there's no partial derivative in the left-hand side. What is dz dt? And the chain rule says this is the partial derivative of, so z is a function of x and y. It's the partial of z with respect to x, dx dt, plus the partial of z with respect to y, dy dt. That's the chain rule. So let me do again an example that I probably have done previously. We have z is the function of x and y given by x squared minus 3y squared plus 20. And suppose x is 2 cosine t and y is 2 sine t. And the problem is to compute dz dt when t is equal to pi over 4. So let me do it using the chain rule, and then we'll check by doing it directly. So dz dt is the partial of z with respect to x. The partial of z with respect to x is 2x times dx dt. The derivative of 2 cosine t is minus 2 sine t, plus the partial of z with respect to y, which is minus 6y, times dy dt, which is 2 cosine t. So we get, let's see, what is x? X is 2 cosine t. So this is 2 times 2 cosine t times minus 2 sine t minus 6y. Y is 2 sine t times 2 cosine t. So this is equal to minus 8 sine t cosine t minus 24 sine t cosine t, which is minus 32 sine t cosine t. And a t equal pi over 4, this is minus 32. The sine and cosine of pi over 4 are both 1 over root 2. So this is equal to 32 over 2 minus, that is minus 16. So using the chain rule, that's the derivative. Now these functions are fairly simple, so I could also just plug in these values for x and y and see what I get. So this is the second method. Kind of a check. So if z is x squared minus 3y squared plus 20, x squared is 2 cosine t squared minus 3 2 sine t squared plus 20. This is equal to 4 cosine squared t minus 12 sine squared t plus 20. So when t is equal to pi over 4, z is 4 cosine of pi over 4 squared minus 12 sine of pi over 4 squared. Each of these is a half. 4 over 2 oops, let's see, did I do, oh, I forgot my plus 20. 2 cosine squared, so it's 4 cosine squared minus 12 sine squared plus 20. That's 4 over 2 minus 12 over 2 plus 20. That's equal to this is 4 over 2 minus 12 over 2 minus 6. So that's equal to, let's see, I never can get my arithmetic right. X squared minus 3y squared plus 20. So, oh, sorry. This is what z is as a function of t. So I forgot to differentiate. dz dt is, differentiate this, you get minus 8 cosine t sine t minus 24 cosine t sine t is minus 32 cosine t sine t, just what we got before. And at t equal to pi over 4, you get minus 16. So it works out. Right? So this is the chain rule, which you certainly have to know. Right? Any questions about that? Okay. So if we have the chain rule, let's try to figure out what the directional derivative is. So we have z is a function of x and y, and we have a unit vector u, u1, u2, and if I look at f of, so I'm looking at, so I want to find the directional derivative in the direction u of the function f at the point a, b. So I take f of a plus, let me use s as the variable because the book does for some reason, f of a plus su1, b plus su2, minus f of ab divided by s. I'm going to take the limit of that as s goes to 0. That's the directional derivative of f at the point AB. And suppose we let g of s be this function, f of a plus su1, b plus su2. So the directional derivative of u at f in the direction of AB is the limit as s goes to 0. This is g of s. This is, when s is 0, minus g of 0 over s. This is just the derivative of g with respect to s. Right? So by the chain rule, the derivative of f in the direction u at the point a, b is dg ds. That's the partial of f with respect to x times derivative of so we're letting x equal a plus su1 and y equal b plus su2. Right. Let me just again start this from the beginning. So I want to try and make it less complicated than it might otherwise be. So here's our problem. We have a unit vector u. We have a point in the plane AB. We take the line through AB in the direction u, and we want to find the directional derivative of u of the function f, the direction derivative of f in the direction u at the point AB. So we go out a certain distance along that line. This is the limit as s goes to 0 of f of a plus su1 comma b plus su2 minus f of ab over s. So suppose I let g of s be this function f of a plus su1 b plus su2. This is really f of x of s comma y of s, where this is x of s and this is y of s. X of s is a plus su1, y of s is b plus su2. So by the chain rule, g prime of s ds dt is the partial of f with respect to x dx ds plus the partial of f with respect to y dy ds. If I take x of s and I differentiate it with respect to s, I just get u1. This is the partial of f with respect to x times u1, partial of f with respect to y, dy ds is u2. And the directional derivative of f in the direction u is the limit as s goes to 0, g of s minus g of 0 over s, that's g prime of s, g prime of 0. So the derivative of f in the direction u is g prime of 0. When s is 0, this is the partial of f with respect to x when s is 0 at a comma b times u1 plus the partial of f with respect to y at ab times u2. And this is the dot product of the partial of f with respect to x at ab, comma, partial of f with respect to y at ab, that vector, dot product with u1, u2. This is just the vector u, and this vector is called, an upside down delta, gradient of f at ab. So this is the dot product of the gradient of f at ab, dot product with u, where what is called the gradient of f at AB is delta f at AB. This means it's the vector where the first coordinate is the partial of f with respect to x at AB, and the second coordinate is the partial of f with respect to y at AB. Now we're going to spend a lot of time in many different areas for the rest of the course dealing with the gradient. But let's use it to compute some directional derivatives. Computing directional derivatives. So the derivative of f in the direction u at AB is the gradient of f at AB, dot product with u. So this is the magic formula you have to remember. So suppose we have z as a function of x and y. It's 1/4 x squared plus 2y squared plus 2. So suppose you take the point P naught, let's say, with coordinates 3, 2, and we take the unit vector 1 over root 2, 1 over root 2. So in the xy plane, it's just this vector along the line y equals x. That's my vector u. So what is the gradient of f? So the partial of f with respect to x at xy, if I differentiate this function with respect to x, I get 1/4 times 2x, or x over 2. So the partial of f with respect to x at the point 3, 2 is equal to 3/2. The partial derivative of this function with respect to y is 1/4 times the derivative of 2y squared, which is 2 times 2y. That's equal to y. So the partial derivative of f with respect to y at the point 3, 2 is 2. So the gradient of f at the point 3, 2, it's fx at 3, 2 I plus fy at 3, 2 j. That's the point 3/2 I plus 2j, or if you just want to write it as coordinates, 3/2 comma 2. That's the gradient of f at 3, 2. So the directional derivative of f at the point 3, 2 in the direction of u is the gradient of f at 3, 2 dot product with u. Gradient of f at 3, 2 is 3/2 comma 2. The vector u has coordinates 1 over root 2, 1 over root 2. When you take the dot product, you get 3/2 times 1 over root 2 plus 2 times 1 over root 2, which is 3 over 2 root 2 plus 2 over root 2, which is the same as 4 over 2 root 2. So that's 7 over 2 root 2. That's the directional derivative. So to check if you are following what's going on, suppose I let v be a different unit vector, the vector 1/2 minus root 3 over 2. So that's a vector which looks like that. That's the vector v. And compute the directional derivative of f in the direction v at the point 3, 2. So I'll pause for a moment and give you a chance to, let's see, how do we do that? Well, the directional derivative in the direction v of f at 3, 2 is the gradient of f at 3, 2 dot product with the vector v. We already computed the gradient. The gradient is 3/2 comma 2, and the vector v is a half minus root 3 over 2. So this is 3/2 times a half plus 2 times minus root 3 over 2. So that's 3/4 minus root 3. Whatever that turns out to be if you write it as a decimal. Okay. Maybe I'll do one or two of the homework problems in this section. So in section 15.5, there's exercise 13, which is we have a simple polynomial f of xy equals 2 plus 3x squared minus 5y squared. And we have the point with coordinates 2 minus 1. And we want to compute the gradient of the function f at the point P. So the partial of f with respect to x is 6x. So the partial of f with respect to P at 2 minus 1 is 12. Differentiate this function with respect to y, you get minus 10y. So the partial of y, partial derivative of f with respect to y at the point 2 minus 1 is minus 10. So the gradient of f at the point 2 minus 1, the first coordinate is the partial of f with respect to x at 2 minus 1. Second coordinate is the partial of f with respect to y at 2 minus 1. And that vector, when x is 2, is 12. And when y is minus 1, when y is minus 1, this is plus 10. Minus 10 times minus 1 is plus 10. 10, 12. That's all it is. In problem number 21, we have the function f of xy equal x squared minus y squared. We take the point P with coordinates minus 1, minus 3, and we take a unit vector u with coordinates 3/5 minus 4/5. And you can check by arithmetic that this really is a unit vector. The sum of the squares of the coordinates is 1. And we want to compute the directional derivative of f in the direction u at the point minus 1, minus 3. And we know this is going to be the gradient of f at minus 1, minus 3, dot product with u. So I need to compute the gradient. For this function, the partial of f with respect to x is 2x. So the partial of f with respect to x at minus 1, minus 3 is 2 times minus 1 or minus 2. The partial of f with respect to y, I differentiate this function with respect to y, I get minus 2y. So the partial of f with respect to y at minus 1, minus 3 is minus 2 times minus 3, or 6. So the gradient of f at minus 1, minus 3 has coordinates minus 2, 6. So the partial derivative of f with respect to u at minus 1, minus 3 is the gradient of f at minus 1, minus 3, dot product with u. The gradient we just computed is minus 2, 6. The vector u is 3/5 minus 4/5. So when you take the dot product, you get minus 6/5 minus 24/5 is minus 30 over 5 is minus 6. So if I did my arithmetic correctly, that's the directional derivative at this point. I want to say some more about understanding and interpreting the gradient. So this is really still in section 15.5. This is interpretations of the gradient. So for every unit vector u, the directional derivative of f in the direction of u at the point AB is the gradient of f at AB dot product with u. But recall, the dot product of two vectors is the product of the lengths of the vectors times the cosine of the angle between them. Right? If this is the vector u, and this is the vector gradient of f at AB, and theta is the angle between these two vectors, this directional derivative is the length of the gradient times the length of u times the cosine of this angle between them. But a unit vector means the length of a vector. This is the definition of a unit vector. It's a vector whose length is 1. That's just 1. So this is the gradient of f at AB times the cosine of theta. And you know that the cosine of theta takes values between -1 and +1, right? If you look at the graph of the cosine of theta, it oscillates between +1 and -1. So when is the directional derivative as large as possible? In what direction? It's in the direction when, so the gradient of the function doesn't vary. That's fixed at the point AB. If you change the unit vector u, the direction of that unit vector, you're changing the angle theta between u and the gradient. The cosine of theta is a maximum, or the maximum value of the cosine of theta is 1. So this directional derivative is at most the gradient of f at AB, because this is at most 1. And the directional derivative of f in the direction of u at the point AB is equal to the gradient of f at AB when theta is 0. Right? You can take theta to be between 0 and pi. As you go from 0 to pi, you go from 1 down to -1, and then it repeats. When theta equals 0, that means the maximum value of the directional derivative is when the angle between the direction and the gradient is 0. That means when u points in the direction of the gradient of f at AB. Or another way of saying this is that f, the function f, has its maximum rate of increase at AB in what direction? In the direction of the gradient. And similarly, what is the smallest this can be? When cosine theta is -1, the directional derivative is greater than or equal to minus this amount. So it has its maximum rate of decrease. I replace increase by decrease. It has its maximum rate in the direction of minus the gradient. Right? So if you know in what if you want to know in what direction a function is increasing most rapidly at a point, it increases most rapidly in the direction of the gradient. And when is the directional derivative 0? So the directional derivative is 0 when cosine of theta is 0. That means theta is pi over 2. So if this is the gradient of f at AB, and this is the unit vector u, we have the directional derivative of f at AB in the direction of u is the magnitude of the gradient vector times the cosine of theta. If the gradient is non-zero, this equals 0 if and only if theta is pi over 2, that is cosine theta is 0. So if you take a direction perpendicular to the gradient, in that direction, the directional derivative is 0. So if you go in any direction orthogonal to or perpendicular to the gradient, the directional derivative of your function is 0. So here's a nice example with pictures in the book. So I'm taking, in my book, this is on page 966, example 4. We have a paraboloid. Paraboloid. This is something you get by rotating a parabola around the y-axis. So we have z as some function of x and y, which is 4 plus 3, the one in the 4 plus x squared plus 3y squared. So that's some surface that looks like that. And if we take f of 2 minus a half, what does that equal to? That's 4 plus x squared, 4 squared, plus 3 times y squared minus a half squared. That's 4 plus 16 plus 3/4. That's, is that right? 4 plus x squared, that's 20, plus 3 times a fourth. Oh, 4 plus 2 squared. X is equal to 2. 4 plus 4, that's 8 plus 3 over 4, that's 35 over 4. So on this parabola, you have the point this is the point in the plane, 2 minus a half, and sitting over it in the parabola is this point on the surface, which has coordinates 2 minus a half 35 over 4, right? Somewhere on the surface. So in what direction from the point 2 minus a half 35 4 on the surface should you move to ascend, go up at the maximum rate? So here you are, there's some point on the surface, and you want to move in some direction on this surface in such a way that you're going up at the maximum rate. So you want to find the maximum value, compute u, so that the directional derivative of f in the direction u at the point 2 minus 1/2 is maximum. And the answer is u in the direction of the gradient of f at the point 2 minus 1/2. So we have to compute the gradient. So if this is my function z, or this f of xy, the partial of f with respect to x is 2x. Partial of f with respect to y is 6y. So the gradient of f at any point xy is 2x 6y. So the gradient of f at the point 2 minus a half is 2 times 2, 4 times minus a half, 4, comma, minus 3. So u, a unit vector, will be a unit vector in the direction of the gradient. That'll be the gradient of f at 2 minus a half divided by the length of the gradient. That gives me a unit vector. If this is the gradient, what is the length of that vector? The coordinates are 4 and minus 3. It's the square root of 4 squared plus minus 3 squared. This is 16 plus 9, square root of 25. That's 5. So this is going to be 4 minus 3 over 5. So the unit vector u, the direction in which we increase most rapidly, is 4/5 minus 3/5. The maximum rate of change it's the vector in the direction of the gradient at 2 minus a half, and the length of that vector we just calculated is 5. just to make this very precise. So the directional derivative of f in the direction u at the point 2 minus 1/2 is the gradient 4 comma minus 3 dot product with this vector 4/5 minus 3/5. That's 16 over 5 plus 9 over 5 is 25 over 5, which is 5, which is just what it's supposed to be. Okay. So again, there's a lot of meat in the mathematics and vector calculus that we're doing now, and a lot of work involved in trying to understand all of this. Let me just point out that I really encourage you to look at the book. In the book, this is the problem I just did. This is the problem. These are very good pictures, or better pictures than one can draw by hand. This is the paraboloid. Here's the point 2 minus 1/2. This is the point on the paraboloid, 2 minus 1/2, 3/5 over 4. And it's showing you the directions of steepest ascent and descent, which are the directions of the gradient. And it's really useful to be studying the book constantly. Okay, let's recall level curves. So if you have a function z equals f of x, y, the graph is a surface in three-dimensional space. But these things are hard, if not impossible, to draw. I'll put hard in quotation marks because sometimes it's not hard. Sometimes you just can't do it by hand. At least most people can't. So a level curve is one way to get some geometrical or visual idea of how the function is changing. So for a fixed number z naught, we have the level curve f of xy equals z naught. So this means in the xy plane, it's some curve, and on this curve, the function takes on the fixed value z naught. That's what's meant by a level curve. It's the set of all points x and y in R2 such that f of xy, the value of the function, is equal to z naught. So in mathematical set theoretical symbols, this is what the level curve is, but it's just all the points where the level curve has a fixed value. And there is a relationship between a level curve and the gradient. So if you have a function z equal f of xy, the function does not change in any direction orthogonal, which is another word for perpendicular, to the gradient of f at that point. So at any point AB, you have a gradient and in any direction perpendicular to the gradient, the function isn't changing. The directional derivative is 0. So I claim, and this is stated in the text as a nice theorem, If you have a function differentiable at AB, it means, for us, it means it has continuous partial derivatives. The tangent line, the line tangent to the level curve of f at AB is orthogonal or perpendicular to the gradient of f at AB if this gradient isn't zero, not the zero vector. So what does this mean? How can I sort of state this in a... So in the xy plane, you have some point AB. And suppose, and the function is defined at this point. So let f at the point AB be equal to z naught. So the value of the function AB is z naught. That means the level curve f of AB equal to z naught, or f of xy equals z naught, passes through the point AB. So this is the level curve, all points for which f of xy equals z naught. And one of those points is AB. That's how we pick z naught. The value of the function of f at AB is z naught. The level curve passes through that point. And if the function is differentiable, or in particular has nice partial derivatives, there's a tangent line to the level curve at the point AB. And the theorem says that this tangent line is perpendicular to the gradient of f at AB. Right? So that's the statement that I want to try to convince you of is true. Let me just draw it like this. Here's the point f of AB. This is the level curve f of xy equals z naught. This is a level curve through AB. At the point AB on this curve, we have a tangent line. At the point AB, this is just y as a function of x. This is all in the xy plane. And I claim that this tangent line is orthogonal or perpendicular to the gradient of f at AB. So here we have this curve on the level curve. So that r of t, the curve x of t comma y of t, be a parametrization of the level curve f of xy equals z naught at the point AB. So near this point AB, every point is of the form x of t comma y of t. And suppose that r at t naught is the point AB. Right? So this is the level curve, which is also parametrized by some vector valued function R of t. So we have f of x, y equals z naught, and x is some function of t, and y is some function of t. And f of x of t, comma, y of t, that's constant. It's always equal to z naught. So differentiate with respect to t. The derivative of a constant with respect to t is 0. That's the derivative with respect to t of f of x of t, comma, y of t. Derivative with respect to t of f of x of t, y of t. And now we use the chain rule. So I want to take the derivative at t equal to t naught. So I take the derivative at the FTT. This is the partial of f with respect to x at x of t naught dx dt plus the partial of f with respect to y at y of t naught dy dt, which is fx at ab dx dt x prime of t plus fy at ab y prime of t. This is the dot product of the gradient of f at ab with r prime of t. If this is r of t, when you differentiate the x and y components. And that's 0. And if the gradient of f is not 0, that means that dot product is 0. It means the two vectors are perpendicular. So gradient of f at AB is orthogonal to r prime of t. But r prime of t, that's just the definition of the tangent vector at the point AB. So what does that say? So here we have, this is AB. This is the tangent line. To the level curve at AB. Here we have the gradient at AB, and these are perpendicular. So if I take a point x, y on the tangent line, this vector is perpendicular to this vector. So that says that the gradient of f at AB dot product with this vector, x minus a, y minus b, is 0. But this is, so this is x minus a, y minus b, dot product with the partial of f at of f with respect to x at AB, partial of f with respect to y at AB, that's 0. Or in other words, partial of x at AB times x minus a plus partial of y at AB times y minus b is 0. So this is another equation of the tangent line. So this is another formula, or this is a formula, if you like, for the tangent line to a level curve at a point AB. So there's a lot going on here. And you can't learn it by watching someone lecture on it. You only learn it by finding a quiet place to work for a couple of hours and studying, and with a lot of paper and pencil. Let's do an example. This is example 6 on page 967 of my book. We have a function f of x, y equal the square root of 1 plus 2x squared plus y squared. We have a point P with coordinates 1, 1. So what is the function f of f? What is the function f evaluated at 1, 1? That's the square root of 1 plus 2 times 1 squared plus 1 squared. That's the square root of 4, which is 2. So we have the level curve f of x, y equals 2. If we want, we could simplify that curve. That's square root of 1 plus 2x squared plus y squared equals 2. If you square both sides, you get 1 plus 2x squared plus y squared equals 4, or 2x squared plus y squared equals 3. So these are equivalent expressions for the level curve. In fact, what this is an ellipse in the plane. Right, so what is the gradient of f at the point 1, 1? So the partial of f with respect to x, if I differentiate this, I get 1/2 1 plus 2x squared plus y squared to the minus 1/2 times the derivative of this, which is 4x. So this is 2x over the square root of 1 plus 2x squared plus y squared. And so the partial derivative of f at the point 1 with respect to x at 1, 1 is 2 over 2, which is 1. The partial of f with respect to y is, when I differentiate this, I get 1/2 1 plus 2x squared plus y squared to the minus 1/2 times 2y. And so the partial of f with respect to y at 1, 1, the 2's cancel, I get 1/2. So the gradient of f at the point 1, 1 is 1, comma, a half. What is the tangent line to the level curve f of x, y equals 2? Or at the point 1, 1, or to the curve 2x squared plus y squared equals 3. at the point 1, 1. What does this curve look like? When x is 0, y is plus or minus 1 over plus or minus root 3. When y is 0, x is plus or minus, x squared is 3 halves. So square root of 3 halves, about 1.2. This curve is an ellipse. And at the point 1, 1, if we differentiate with respect to x, we get 2 times 2x, implicit differentiation, plus 2y dy dx equals 0. So dy dx is minus 4x over 2y, which is minus 2x over y. And if you evaluate this at the point 1, 1, you get minus 2. And the gradient is 1.5. So if you take a line, the direction of the gradient, this line has slope 1/2. The tangent line to the ellipse at this point is slope minus 2. Minus 2 times 1/2 is minus 1. Two lines are perpendicular if the product of their slopes is minus 1. So this is one way to see that these are perpendicular. Let me go through it a slightly different way. So we have the level curve f of x, y equal 2 is the ellipse 2x squared plus y squared equals 3. So one point on that is the point 1, 1, of course, because 2 plus 1 is 3. And this is the level curve. What is the tangent line to the curve at this point? So it's the line through 1, 1 with slope dy dx at that point. By implicit differentiation, when I differentiate with respect to x, I get 2 times 2x plus 2y dy dx equals 0. So dy dx is equal to minus 4x over 2y, or minus 2x over y. So dy dx at the point 1, 1 is minus 2. So the tangent line has slope minus 2. It goes through the point 1, 1, so the equation is, so what is the point slope formula? If you take y minus 1 is the slope minus 2 times x minus 1, or y equals minus 2x plus 3. It's the equation of the tangent line to this level curve. So the tangent line, which is the tangent line to the level curve f of xy equals 1. And the gradient of f at the point 1, 1, we calculated, and it's equal to 1.5. That's the gradient. And any point on the line in the direction of the gradient where that line has slope a half. And a half and -2 multiply out to be -1. So the gradient of f at 1, 1 is perpendicular or orthogonal to the tangent line with a level curve. Now, in 3 dimensions, put this on a sheet of paper, just in 3 dimensions, basically nothing changes. So if we have w is a function of x, y, and z, the gradient of this function f at any point a, b, c, it's a vector whose coordinates are the partial derivative of f with respect to x, partial derivative of f with respect to y, and partial derivative of z, of f with respect to z, all at that same point. That's the gradient. And if you have a unit vector u with coordinates u1, u2, u3, the directional derivative of f in the direction of u at any point x, y, z is the gradient of f in that direction. Sorry, is the gradient of f at that point, dot product with the direction u. The maximum rate of increase of a function of 3 variables is in the direction of the gradient. The minimum rate of increase is in the direction of minus the gradient, and the rate of change of the function at a point is 0 in any direction orthogonal to the gradient. So if we want to look at one example of this, suppose we have a function of 3 variables. F of x, y, z is x squared plus 2y squared plus 4z squared minus 1. And we have a level surface of f of x, y, z equal 3. The analog to a level curve in the plane is a level surface in 3-dimensional space. So, and notice that f of 2, 0, 0 is 2 squared plus 0 minus 1 or 3. So this level surface passes through the point 2, 0, 0. And the gradient of f, you take the partial of f with respect to x, that's 2x. Partial of f with respect to y is 4y. Partial of f with respect to z is 8z. So the gradient of f at the point 2, 0, 0 is 4, 0, 0. This level surface is an ellipsoid. It's impossible to draw. But if you want the directional derivative in some point, you just take the dot product of the gradient with the unit vector in that direction. That's what it is. So all I can suggest is to do the following 3 things. First, study the book. Second, study the book. And third, do many, many problems, including all of the examples in the book. That is, the book will state a problem. I did most of the problems here, but look at the book. It's legible, it's clear. And work through line by line, word by word, everything that the book is saying about how you solve these problems. And then you will understand what's going on and do well in the exam, and not otherwise, I guess. Any questions about this? I mean, we're covering, there's a lot of material in vector calculus, and we're entering now the second half of the semester, which is when the level of what we're doing increases. All of the easy stuff we got out of the way, where we went by, and now things get more and more interesting, if you like, or complicated, if you don't like. Any questions? Again, I have numerous office hours problem sessions this week, and I encourage you to log in and ask questions, no matter how elementary or silly or whatever you think they might be. But questions are always good, so I encourage you to ask. Okay. If there are no more questions, or if there are no questions, we're done for today. And on Wednesday, we'll learn about tangent planes. So that's pretty good. Okay. Keep in mind that the second exam is probably in just maybe 3 weeks. So it's not that far away. Okay. All right. Enjoy the day. See you Wednesday. Bye all.